Okay, so these are the test three solutions. So problem one, you asked to find the cross-sectional volume of between the two functions, -2 plus 3 cosine pi over 2x and h of x equals 6 minus 2x minus 1 squared. And then it was bounded by x equals 0 and x equals 2. So you've got this picture here, you got the labeled slice. And you wanted to find cross-sectional volume, so I wrote the formula, which is the integral of whatever the area function is with respect to dx. So the area function you gave us was 1 over 3x plus 1. And the limits of integration are from 0 to 2 because that's what it said in the problem. So in my second line of work, you can see it's from -2 or 0 to -2, 1 over 3x plus 1 dx. And then I took the integral of that, which is ln of whatever is underneath. So I got 3 ln of 3x plus 1. The reason there's a 3 in front is because of the chain rule. I took the derivative of 3x plus 1, which is 3, put that in front. And then after that, I did fundamental theorem part 2. So I distributed the 2, and then I distributed the 0. Did a bit of algebra. I got 3 ln 6 plus 1 minus 3 ln of 1. And that's just 0, so that goes away. So in the end, I got the volume is equal to 3 ln of 7 units cubed for problem number 1. Okay. Problem number 2. So you have to find the volume of the region bounded by these two functions, rotated about the line y equals 5. So you can see the axis of rotation up here. And here's the pick with labeled slice and the two functions drawn out best I could. And so first I found the limits of integration just because that'll be useful for us later. So I set the two functions equal to each other, did some algebra, some factoring. I got x equals -1 and x equals 4, so that'd be very helpful for us. And obviously, since we're doing a rotation problem, we have the formula v equals integral of pi r squared dx, and this is perpendicular. So also, we know this is a washer because the function does not touch the axis of rotation in certain places, actually all places. So we have to subtract the big area minus the small area because that's how you do the washer method. So I just wrote out the formula and plugged in a respective function. So we got 5 minus y2 squared. That's the big because it goes from the top axis rotation down to the bottom function. Y2 will later be substituted for the actual function. We'll do that a bit later though. And then small, the small part is the empty part that we want to subtract because that doesn't actually count towards the volume between the two curves. So that would be 5 minus y1 squared with respect to dx because you just plug in the formula and the radius is 5 minus y1 squared. So oops, sorry about that. So then after that, I substituted y2, plugged in the actual function, substituted y1, plugged in the actual function. We've got our limits of integration 4 to -1, obviously. I factored out the pi because it makes things a bit easier. So then we did some algebra, simplified a little. I got to -x squared plus 2x plus 13 squared, x squared minus 4x plus 5 squared. And then I have to square that because you can't find the integral without simplifying the term. So I did that, took a bit of algebra. Then after that I found the antiderivative. And then I used fundamental theorem part 2, as you can see. I couldn't fit everything into one piece of notebook paper, so I drew some arrows. So the second part, this part right here, I saved for later. And yeah, so I took the integral, plugged in the numbers, did some algebra, did a lot of arithmetic until I solved it all the way down to the volume, which is 625 pi units cubed. I put the pi in there. I just forgot to put in my final answer, but yes, it is 625 pi units cubed for my final rotational volume for number 2. Okay, number 3. Number 3, find the volume of the solid generated by revolving the region. So this is another rotational volume problem, but in this one, I used the disk method. I did not use washers because there's no gaps in between the axis of rotation and the curve. So there's my pick with labeled slice. You can see that's 0. The function is this. Formula here. Limits of integration, obviously from 0 to 4 because it says in the problem. So I plugged in my function, square root of e to the negative square root of x over square root of x, squared it, and then obviously you have to take the integral. So this is where I use u substitution. So my u is equal to square root of x, and my du is obviously the derivative of that, 1 over 2 root x dx. And then I did a little bit of algebra manipulation so that I could properly substitute. So I got negative 2 root x du equals dx. And so I plugged in the respective variables into the integral. So I ended up with e to the u over root x times negative 2 root x du. There's some nice cancellation. So then I end up with integral negative 2 e to the u du. The negative 2 because it's a constant. And then I obviously took the integral e to the u, integral of e to the u is e to the u. So then I get negative 2 e to the negative root x. I plug that into the back into the regular integral function, and then I do fundamental theorem part 2, plug in the numbers, do some algebra. I just solve, and then I simplify until I get everything under one fraction. So the answer, the volume is negative 2 pi plus 2 pi e squared over e squared units cubed for number 3. Okay, number 4. So limit as x approaches 0 from the right of sine x to the x power. So if you just plug that in using direct substitution, you get 0 to the 0, which is an indeterminate form. So I'm going to take the natural log of that so I can bring the x power to the front. So I get x ln in parentheses sine x. So then I take the x and I put it underneath so that I can get L'Hopital's rule. So that when you plug in 0 after that, you get infinity over infinity, because sine of 0 is equal to 0, and then ln of 0 goes to infinity. So it's 0 of 0, L'Hopital's rule. So then you take the derivative of that, which you can see in this step. Derivative of sine is 1 over times the inside of the function because it's chain rule. And then obviously at the derivative of the bottom is what it is. You can simplify that to cotangent of x on the top, and then negative 1 over x squared. So then I flipped it for further simplification. Took the negative out, and I plugged it back in. You get another L'Hopital's rule, so I took the derivative again. And then finally, it's not an indeterminate form anymore. I brought the secant squared up to make it cosine squared x. I plugged in the 0. So then the answer after that, I got 0. But remember, I put the ln, so I have to re-exponentiate it. And so e to the 0 equals 1. So that's problem number 4. Problem number 5, write the equation for the normal probability density function. So I get these 5 numbers. I took the mean, which I got 6. Then to find the standard deviation, I subtracted the mean from the original numbers, squared those numbers, then found the new mean and square rooted it, which I got standard deviation. And then I plugged it into the normal probability equation, which obviously is here 1 over sigma root 2 pi e to the negative x minus mu squared over 2 sigma squared. Plugged in root 2 for sigma and 6 for mu. Did some simple algebra, simplified until I was able to get to the answer, which is 1 over 2 root pi. 2 root pi e to the negative x minus 6 squared over 4. So that's problem number 5. Problem number 6, it's pertaining to the last question. What percentage of the data are between 2 and 3 standard deviations greater than the mean? So just using the standard deviation rules, 2 standard deviations away from the mean, in either direction you get 95%, 3 away from the mean you get 99.7%, but we're only looking at the stuff that's greater than the mean, so you half those percentages. So we're finding what is in between 2 and 3 standard deviations greater than the mean. So I subtracted 3 standard deviations from 2 standard deviations, which gets me 4.7%. And since we're only concerned with anything between 2 and 3 standard deviations greater than the mean, I divided by 2, which gives me 2.35%. And so that percentage of data is between 2 and 3 standard deviations greater than the mean, using what we know about standard deviations already and the respective percentages in all standard deviation functions. Okay, problem, excuse me, number 7. It was a work problem. So for the first part, you asked what the amount of work it would take to lift the bucket alone. So the bucket weighed 200 newtons, 50 feet. Work is force times distance, so 200 times 50 is 10,000. So then after that, I wanted to solve how much work it would take to lift the water. So at it's slowly leaking constantly, right? So at 0 newtons, or at 0 meters, or 0 feet, sorry, the water weighs 100 newtons, and at 50 feet at the top, the water weighs 0 newtons. So you can take the equation of that line. So I found the slope, which was -2. I did the y minus y1 equals mx minus x1 to find an equation of the line, which I got y equals -2x plus 100. And obviously the limits of integration are from 0 to 50 because the bucket and the water goes from 0 to 50 feet. And so I took the integral of the equation of the line, which I got -x squared plus 100x, limits 50 to 0, plugged in those numbers. Obviously, I used fundamental theorem part 2. The zeros cancel out. And then you get just addition here. So the work it takes to lift the water is 2,500 newtons. Finally, you need to figure out the rope. So the rope is weighs 0.8 newtons per foot, and you have 50 feet of rope. So total, it weighs 40 newtons when it's at the bottom. And since you're pulling the rope up, it gets less and less weight. So at the top, the rope weighs 0, or the rope, weighs 0 newtons at 50 feet. So you find the slope of that, -4/5. You plug it into the equation of the line. You do the same thing that you did when you want to lift the water. So I took the antiderivative, -2/5 x squared plus 40x. Did fundamental theorem part 2, plugged it in, did some addition, subtraction, and I got 1,000 newtons per feet, or 1,000 newton feet. And so to find the total work of all of that, you just add all 3 together, so I got 13,500 newton feet for number 7. Okay, number 8, you want to find the arc length of this function here. So the arc length formula is square root of 1 plus f prime of x squared, obviously with the integrals. So the integral of f of x, integral x to the top function, you use fundamental theorem part 1, so I just replaced the t with the x to take the derivative. So the integral disappears, and you're just left with square root of x cubed minus 1 because of fundamental theorem part 1. And then I squared that, so you get x cubed minus 1. And obviously the limits of integration are from 4 to 6 because that's what it says in the problem. So then you just get x cubed. You take the antiderivative of square root of x cubed. You get 2/5 x to the 5/2 from 6 to 4. You use fundamental theorem part 2. You try to do some simplification. It doesn't simplify all the way, unfortunately. So you get 2/5 to the 5th root 36 minus 2/5 5th root 16. I factored out the 2/5 just as an attempt at simplification. And for your final answer, you get 2/5 times 5th root 36 minus 5th root 16 units. And that is the arc length of number 8. So that is all.